Hey everyone, welcome back to the Code Path YouTube channel. Have you ever wondered how we store and search data effectively? There is a data structure that we can accomplish these both together. Meet the binary search trees, a powerful data structure that makes searching super fast and efficient. In this video, we'll break down what BSTs or binary search trees and how they work and implement them in code. So let's get started. Before we dive in, let's take a look at what we'll be learning in this video. Before we dive in, let's take a look at what we'll be learning in this video. First, we'll understand what a binary search tree is and why it's such an important data structure in computer science. Next, we'll explore the fundamental operations like insertion, deletion, and searching in a BST. We won't just talk theory. We'll also write and run actual code to implement a BST from scratch. Finally, we'll break down the time complexity of BST operations and understand when it performs best. Sounds excited? Let's get started. A binary search tree is a special kind of binary tree where each node follows these rules. The left subtree contains values smaller than the parent. The right subtree contains values greater than the parent. Each node has at most two children. For example, in this BST, notice how every left child is smaller and every right child is greater. Binary search trees support four main operations. Number one, insertion. Add in a new value. Deletion is operation that is used to remove a value. Search. Checking if a value exists. Traversal is the operation used to visit all elements in order, pre-order or post-order. In this part, we are going to cover the basics of binary search trees and we are going to implement one using Java step by step. First, we are going to define a node class. This class is going to contain three attributes: the key or the value, a reference to the left child, and a reference to the right child. Then we are going to initialize the constructor. So by the constructor, a new node will be given the key and both children are going to be null initially. Next, we define the binary search tree class. We initialize an empty tree by setting the root node to null. To insert a new value into the BST, we are going to create a method insert. And we are going to pass the integer value. In the insert method, we are going to call a recursive function named insert rec. If the current node is null, we create a new node and place the key there. So this part is going to be the base statement of our recursion function. Then we are going to write the recursive statement. Okay, next we will implement the search function. The search function allows us to find if a key exists in the BST or not. For that, we have to use a recursive helper function. We are going to call it search. So, the return type of the search function will be Boolean, because we need to find if whether there is a value or not. Return the recursive function. We are going to pass the root and the value as parameters. Same goes to the recursion function. The return data type will be Boolean. Search rec passing the root and the value. Then we are going to write the base statement of our recursion function. If we have found a value same as the value we have passed, we are going to return true. Then let's write the recursive statement. For a better code, we are going to use ternary operator here. We are going to pass the left value and the right value. So that's basically the search function in our binary search tree. Next, to display the BST in a sorted order, we are going to use an in-order traversal. The in-order function is going to call in-order rec, which is recursive, and it is going to visit the left subtree recursively, and it's going to print the node value, and then it is going to exit, and then it's going to visit the right subtree. So the in-order method is going to be void we are going to call the recursion function here in order rec. and we are going to pass the root. Now let's create the inOrderRec function here. We have to pass a node which is the root, and please check if the root is not null and carry on the next the traversal, and it will carry on the traversal, first visiting the left subtree and then visiting the right subtree. Then it's going to visit the rightmost subtree. There you have it. The inOrder function is done. And finally, in the main method, we'll create a object using BST and insert some values. Then we can perform an inOrder traversal to see the sorted number of elements. Then we will test the search function by looking for a specific key in the BST. Let's run this program and see whether the traversal is done correctly and the search function is done correctly. Now let's run the program and see whether our inOrder traversal and the search functions are working or not. As you can see, we have got a sorted array here, and we have performed two search functions. You can see we have 40 here, and we have got true as the return and 100 as false. Now let's analyze how fast BST operations are. If the BST is balanced, we get efficient performance. Insertion, search and deletion all run in O into log n time. Tree traversals like inOrder, pre-order and post-order take big O into n time since we visit every node. In worst case, or if the tree is unbalanced, the performance degrades. Insertion, search and deletion can take big O into n time instead of big O into log n. That's why keeping the BST balanced is so important.